The electromagnetic spectrum. Electromagnetic waves and what they mean to us. This image illustrates what an electromagnetic wave looks like. They have two parts as the name suggests, the electric and magnetic, E and B respectively. EM waves travel at the speed of light with a certain frequency and wavelength. See this equation C equals F times lambda. Therefore, as frequency increases, wavelength decreases. This means we have many different types of electromagnetic waves with different frequencies and wavelengths, as we will further dive into. Here's a reminder of three things that can happen to waves when they encounter a material. First is transmission. This is the ability of the wave to pass through a material or not. Reflection. This is when the wave bounces off the material. Absorption. This is when the wave and the material have some sort of interaction that stops the wave from propagating. Think like a sponge soaking up water. Here's another example of these three. There are three rules of thumb when it comes to EM waves. First, high-frequency electromagnetic waves, like the one with the arrow pointing to it in the above photo, are more energetic and are more able to penetrate than low-frequency waves. Second, high-frequency EM waves can carry more information per unit time than low-frequency waves. Third, the shorter the wavelength of any electromagnetic wave probing a material, the smaller the detail it is possible to resolve. Here's the electromagnetic spectrum. It shows all the different kinds of waves with their wavelengths and frequencies. We will go through each of these in this video. What I want to point out here in the photo on the right is that there is a bit of overlap between some of the wave spectrums. Radio waves. The general definition for these waves is that they're produced by currents in wires and circuits. But we also have radio waves that come from space, which instead are produced by astronomical phenomena. So, what are some examples of radio waves? AM and FM radio, TV, cell phones, and radio waves from space. This last photo shows a bit what the difference in frequency and wavelength might look like for different radio waves. AM and FM are two different ways to transmit information through waves. AM radio waves carry commercial radio signals, and AM stands for amplitude modulation. They take a carrier wave with basic frequency in the kilohertz range, put audio into it, and the amplitude of the resulting wave is then modulated. AM waves have constant frequency, but varying amplitude. FM radio waves also carry commercial radio transmission. FM stands for frequency modulation. They take a carrier wave with basic frequency in the megahertz range, put in an audio signal, and the resulting wave has slightly different frequency. FM waves have constant amplitude, but varying frequency. Remember that waves' amplitudes can add. This therefore makes AM radio more susceptible to added noise, changing the amplitude transmitted, which is why AM sometimes sounds fuzzier, while FM sounds clearer, because FM can focus on just the frequency variation. TV uses different ranges of frequencies to achieve picture and sound, very high frequency or ultra high frequency. If you're using an old-fashioned roof antenna, TV video signals are AM, while TV audio is FM. If you're using satellite or cable, transmission of TV occurs at significantly higher frequencies. Why are we asked to put our phones on airplane mode on the plane or turn them off in hospitals or theaters? Besides the obvious disturbance of someone getting a phone call during a play or movie, or privacy issues in the hospital, phones may operate on a similar frequency to the communications or medical equipment and therefore cause interference, which can be dangerous. Those working want to minimize that interference by having you turn off your phone. In short, if you're asked to turn off your phone in a plane or hospital, do it. Microwaves are the highest frequency EM waves that can be produced by currents in macroscopic circuits and devices. Microwaves have short wavelengths compared to other radio waves. That's where the micro in microwave comes from. These waves are produced by atoms and molecules generated by thermal agitation. The thermal motion of atoms and molecules in any object at a temperature above absolute zero causes them to emit and absorb radiation. There are three major applications of microwaves. 1. Heating. Microwaves at a frequency of 2.5 gigahertz are produced by accelerating electrons, which are then used to induce an alternating electric field in the oven. The range of microwave oven frequencies is selected so that polar molecules, such as water, absorb these energies and increase their temperatures. This is why the thermal agitation leads to hot food and not a hot plate, which does not contain water. Communications. This includes satellite transmitted information, as well as land-based long-distance transmissions. However, the second one requires a clear line of sight between transmitter and receiver. Radar. Radar detects and times microwave echoes to determine the distance to objects, whether the object be a cloud, an aircraft, etc. Speed can also be determined using a Doppler shift in the radar echo. It can also map the Earth and other planets. Remember, the shorter the wavelength, the smaller the detail that it's possible to observe. Infrared radiation. IR has higher frequencies than microwaves. It can overlap slightly with microwave frequencies, but it stops just below the frequency for red and visible light. IR is produced by thermal motion and the vibration and rotation of atoms and molecules. It is particularly good at detecting water molecules' rotation and vibration. Applications. First, night vision. You can detect infrared emitted by various warm objects, including humans, and convert it to visible light. Reconnaissance. Detect buildings, vehicles, and even individual humans. Very useful in police or military situations. Heating. Infrared lamps can warm us because we absorb infrared better than our surroundings. The Earth also gives off infrared radiation, some of which exits through the atmosphere and some of which is reflected back onto the Earth, called the greenhouse effect, which keeps Earth warm. Burning of fossil fuels and other things that cause greenhouse gas emissions seem to have increased global temperature more than it has been heated in the past. We call this effect climate change. Visible light. The frequency range of visible light is 4 to 7.5 times 10 to the 14th hertz. However, it is more commonly recognized by its wavelength, 400 to 750 nanometers. Visible light is named so because it is detectable by the human eye. The colors that we detect depend on what wavelengths or frequencies the object absorbs or reflects. Things that appear green reflect green. Things that appear black absorb all color. It is produced by vibrations and motions of atoms and molecules, as well as the electronic transitions within them. Receivers/detectors of light largely use electronic transitions. Light goes through two major transitions, excitement and relaxation. Excitement is absorption of electronic transmissions. Relaxation is emission of electronic transmissions. Humans and plants use the visible spectrum slightly differently. Humans use all parts of the visible spectrum. Plants are more selective. Photosynthesis makes use of parts of the visible spectrum to make sugars. Side note, visible light has both particle and wave nature depending on how it is observed and what it is interacting with. UV radiation. It is produced by atomic and molecular motions and electronic transitions. There are three major categories of UV radiation. First, UVA. 99% of all UV light from the sun that makes it into Earth's atmosphere is UVA. Second, UVB. Only a small portion of UVB gets through the Earth's atmosphere. Third is UVC. Most UVB and all UVC is absorbed by the ozone molecules in Earth's upper atmosphere. Things to note. UV radiation can have adverse effects. It can damage collagen fibers. For UVA, this means it penetrates through the top layer of skin and leads to aging and wrinkles by affecting the deeper layers of the skin. Even though not much UVB makes it through the atmosphere, exposing yourself to UVB that does make it through can lead to skin cancer, sunburns, and cataracts. Large exposure leads to temporary sunburns. Repeated exposure leads to skin cancer and cataracts. So then why are so many people trying to be tan? In the 1950s, tanning became a sign of the elite and wealthy because they could afford the leisure time to go on vacation and relax and tan. Now, a tan is often a symbol of the currently desirable outdoorsy travel lifestyle. Why can't we use flash photography to take pictures of precious artwork? The UV radiation from the flash can cause photodegradation of the artwork. However, not all UV radiation is bad. Some of the benefits include vitamin D production in the skin as a result of UVB exposure, and vitamin D is important for bone health, as well as the reduction of prostate, breast, and colon cancer. About 10 minutes every day without sunscreen is the recommended level. UV radiation can be used for sterilization of tools to kill germs. It can also be used for microscopy to detect details smaller than those observable by visible light microscopes. X-rays. X-rays are produced through high voltage electrical discharges. They can penetrate many materials and do so differently depending on material density. X-rays have both positive and negative aspects. Some of the benefits include the ability to image objects that are opaque to visible light, with the most well-known version of this being screening the human body. This field of medicine involves X-rays and the human body is called radiology. Another benefit is X-ray crystallography, which allows people to determine the structure of tiny molecules such as DNA. There are a few drawbacks to X-rays, such as they are more penetrating than UV radiation, so they have negative effects on living cells that can lead to cancer and genetic defects if there is too much exposure. This is why doctors, quote, hide when they take your X-rays, because if the doctor stood in front of the X-ray all day for 45 years, they would experience lethal amounts of X-rays, whereas you may only experience a few minutes of X-ray radiation in your lifetime, most of it blocked by the lead apron, such as in this picture. Gamma rays. This is the most penetrating type of radiation emitted by a nucleus, similar to the penetration of X-rays. Gamma rays occur from the radioactive decay of an atom. These rays are damaging to living tissues, but can therefore be used for cancer therapy to target the cancer. They can also be used in scanning luggage at airports. The entire EM spectrum is used to investigate stars, space, and time. Microwaves help identify background radiation coming from the Big Bang. The Hubble Space Telescope gathers UV radiation and visible light to see objects far from Earth in our galaxy. There are additional telescopes focusing on radio waves, infrared radiation, X-rays, and gamma rays. In conclusion, knowing about the electromagnetic spectrum helps us better understand and experience the world and space around us.